All right, so this is chapter 9 in the OpenStax textbook. Um, if you're taking my class, just make sure it's possible that I may have pushed this chapter earlier in the order of things. So um, um, anyway, chapter 9 is the gaseous state. So um, when we say atoms and molecules, we know they're teeny tiny things, but how do we really know they're there? We don't have experience with them. We can't see them. So what we see is the collection of these atoms and molecules that make up gases, liquids, and solids. So we're looking at the macroscopic collection of all of these atoms, and we can see how they react, how gases react, liquids, solids react. And so it's not obvious that these things are made up of atoms or molecules. Anyway, what we're going to do is if we understand how nature works, how matter works, then we can apply what we know about these atoms and molecules. We can apply the nature of the matter to that, and how then we can explain what atoms and molecules are doing to give rise to the properties that we observe. Now, liquids and solids can be very complicated, but gases are very straightforward, or pretty straightforward. So that's why we start talking with gases first, because they kind of go straightforward. So we're gonna start by talking about the gaseous state. So again, the gases are the easiest to understand. They have few deviations, and so that's why we start with them. All compounds that are gases at room temperature will be non-metallic elements. They have very low molecular weights, and they have very simple formulas. If anything is a bigger molecule, they will tend not to be gases. They'll tend to be liquids or solids at room temperature. So the gases that we may be talking about, HCN is hydrogen cyanide as a gas, H2S, hydrogen sulfide, CO, carbon monoxide, CO2, carbon dioxide, CH4 is methane, natural gas, SO2, sulfur dioxide, which is the smell of rotten eggs, C3H8 is propane, so that's also a gas at room temperature. There's also ethane, but propane's more common. Oxygen gas, nitrogen gas, NO2, nitrogen dioxide. So we already know that gases differ from liquids and solids. We know that gases expand to fill a container, to fit a container, fill a container. Gases are highly compressible, and so if you apply pressure, you can compress gases down because they have lots of empty space. Gases will form homogeneous mixtures with each other no matter what they are. So if you have two gases and you put them in the same container, eventually they'll mix and become homogeneous mixture. They'll be spread out evenly. And so, like I just said a minute ago, molecules of gas molecules tend to be very far apart, and so they act independently of each other. And so what we're going to do in this chapter is look at the quantitative relationships of gases, or sometimes we call those the empirical gas laws. And then we're also going to look at the ideal gas law, empirical gas laws. But first, before we, since we're going to be talking about pressure, let's understand the idea of pressure. So you probably already know the word. Pressure, if I put pressure on something, I'm pushing on it. It's a force exerted, but it also will depend on the unit area. So, if I put my little finger on something and press a big thing, it's not going to have very much pressure. Whereas if I have a small ping pong ball or something and I push it with all my might, it's going to go very far. So pressure has that force per unit area is our measure. So one way when we're talking about gases, one thing you can think about with pressure is if you've got a container filled with a gas, we can think of pressure as how often and how hard molecules hit the container they're in. So that's something to consider. So atmospheric is the pressure of the air molecules as they are pulled toward the Earth by gravity. So we can feel the air molecules being pulled down, and they apply pressure to us. But of course, air molecules are teeny tiny, and they're moving very fast. They have a lot of energy, and so actually they can fight gravity a little bit. So if they couldn't, then the layer of air on Earth would be very, very low, and we wouldn't have life on Earth. So the atmosphere is very large because gravity can't pull super hard on those molecules. The atmosphere exerts a pressure roughly equal to the weight of a bowling ball pressing on an area the size of a human thumbnail. That's kind of heavy. It doesn't feel like much, but the pressure on us is pretty hard, pretty great. Here are some conversion factors that you'll probably want to know. I would say the second one here is probably more likely. So 1 atmosphere, so I guess the English unit is pounds per square inch, or PSI, so that's what we tend to use, like when we fill up our tires and things like that. And 1 atmosphere equals 14.7 PSI. Most of the time you'll be given units, either atmospheres, which is a standard pressure is in atmospheres. Let me change the color here. 1 atmosphere is equal to 760 millimeters of mercury. That's what the mm of mercury, which I'll explain in just a minute. Probably the most common unit is actually 760 torr. Actually, atmosphere is most common, 760 torr. So millimeters of mercury and torr are actually the same unit. Millimeters of mercury, torr was named for an Italian scientist, so that's where that comes from. So 760 torr or 760 millimeters of mercury are the same, and then they equal 1 atmosphere. All right, so this is a mercury barometer. So this was originally how atmospheric pressure was measured. So you can see here that, I gotta go back to my purple here. So you've got this container full of mercury. And then if you take this tube and you fill it to the tippy top with mercury and then turn it upside down into this bowl of mercury, some of the mercury will start to run out, right? Because it's open in here. But then eventually it will stop. Why does it stop? Because atmospheric pressure is pushing down on the surface of the mercury. So if we measure the height of the mercury, and this is where 760 millimeters of mercury comes from, is standard pressure is when this height is 760 millimeters. Now, that doesn't mean that's always the temperature. What happens if atmospheric pressure lowers? If it stops pushing quite as hard, then some more of the liquid will run out and the pressure will lower. So if atmospheric drops, this column of mercury will also drop. If atmospheric pressure increases, it'll push harder on there, and the tube will, the column of mercury will rise. So like I said, commonly the pressure of the atmosphere at sea level pushes the column to a height of 760 millimeters of mercury. So that's what that unit is, 670 millimeters of mercury, which is the same as 760 torr. 1 millimeter of mercury equals 1 torr. Interestingly, mercury is used because it's such a dense liquid. It's really the densest pure liquid that we have. I'm sure there may be others, but way back when it wasn't. So in fact, if you tried to make a barometer using water, I found this really interesting. The column of liquid used is, again, it's the same process. You've got atmospheric pressure pushing down, and then you have a tube of liquid. So because mercury is so much more dense, you can have a short column to measure. So it's actually 760, pretty tall, maybe that's about 3 feet tall or something like that. So it's still not short, but if you tried to have water as the liquid, because air pressure will push easier, the water will go up easier from the air pressure, you actually have to have, there's the 760 milliliters is a little less than 3 feet, 2.5 feet. to have a similar measurement for water, the barometer would have to be almost 34 feet tall, so it's not very practical. So that's why we have mercury barometers. Well, not anymore, but way back when they did, because of it's easier to read. Okay, so we're going to look at the empirical gas laws. At constant temperature and pressure, a gas will expand uniformly to fill the container in which it's contained. But if we change the temperature, if we change the pressure, then the volume will also change. So all gases have the same dependence on these four properties: volume, amount, temperature, and pressure. So the first relationship, or the empirical gas law that we're going to look at, is Boyle's law. And Boyle's law compares volume and pressure. So notice that it's at a given temperature. So temperature's constant. And so the volume of a sample will vary inversely with pressure. So in other words, so this is a way of writing it. Volume is directly related to 1 over pressure, or indirectly related to pressure, which means 1 over pressure is directly related. So as pressure goes up, volume will come down. As volume goes up, pressure goes down. So that is inversely related, and this is the relationship. Volume is equal to some constant over pressure, so they're inversely related. Keep in mind that, again, constant temperature is not changing, and the amount of gas is not changing. We're not adding or taking any away. And so as pressure increases, volume decreases in pressure. So this is an indirect relationship, and this is another way of saying it. So if we have a certain pressure and volume, and then we change one or the other, the other will change. So let's say I have a particular pressure and volume, and then I increase the pressure, the volume will decrease. And this relationship will hold. P1V1 equals P2V2. You might want to look at some of these little links separately if you're interested. So here's an example. So here we have a kind of yellow's not going to work there. Here we have a small pressure and we have a larger volume, so the volume of the gas. Now if we increase the pressure, so we put higher pressure on there, then what's going to happen? You can see that the volume decreases. So or you can think of it in the opposite way. If we in order to increase the volume here, we're going to have to decrease the pressure. So they're inversely related. Breathing is an example of Boyle's law. When you breathe in, what you're supposed to do, of course, is expand your stomach, expand your diaphragm. Your diaphragm expands, it goes down, your lungs get bigger, so that increases the volume. Now this means the pressure will decrease, so suddenly the pressure inside your lungs will be lower, and it's lower than the outside pressure. So then the pressure from the outside will quickly go into your lungs. When you breathe out, you're decreasing the volume of your lungs, and so the pressure increases inside your lungs. So now the pressure inside your lungs is higher than outside your body, and the air will naturally flow out. So that's Boyle's law. Since it's an inverse relationship, if we plot volume versus pressure, we get this kind of relationship, and that's an inverse relationship. And like I said, if you then take volume and you plot it versus 1 over pressure, so you invert pressure, that's an inverse relationship, you'll get a straight line. So volume is directly related to 1 over pressure. But overall, it's an indirect relationship of volume and pressure. Okay, so let's look at a quick example. Sample of chlorine gas has a volume of 1.8 liters at 1.0 atmosphere. If the pressure increases to 4 atmospheres, and again at constant temperature, that's important, what would the new volume be? All right, so we're going to use our Boyle's law. P1 times V1 equals P2 times V2. It doesn't matter which ones are 1s and 2s. We tend to think of 1s as our starting and 2s as our final. The critical thing is to make sure you have the correct ones that go on the same side. So 1.8 liter is my initial volume, so V1. The pressure at my initial pressure is P1. So these two go together. At's kind of a linking. And then I'm going to raise my pressure to 2 atmospheres. So that's P2. And then what am I looking for? I'm looking for my new volume, which is V2. So as long as, now if I called these 1s and these 2s, it wouldn't matter as long as they're on the same side. So here, if you see, I actually rearranged the equation. So I divided both sides by P2 and got V1, V2 is P1 times V1 over P2. So I plugged those values in, and you can solve for so the answer is 0.45 liters. Notice that the atmospheres cancel because those are the same units, and then the liter is the unit that's left over. Sometimes people like to just plug the numbers in first and then do the algebra rearranging, especially if you have more than 2 factors on each side. You'll see when we get to a little bit harder one. So if I've got the 1.8 liters and I've got the P1 1.0, and then on this side I have 4.0, and I'm looking for volume. So I can, now this one's a pretty straightforward one, so I can do my math here. 1.8 equals 4V, and then I want to get V by myself, so I divide both sides by V, and I get V equals 0.45 liters. Which is the units that I started with. I do want to mention you have to be careful. It doesn't matter what units you use. However, you do have to make sure they're the same. So in this case, both pressures are in ATMs. The volume is in liters, so my new answer will be in liters. If you're given different units, you need to make sure and convert one of them to the other. It doesn't matter which, but they have to be the same for them to cancel out. And also, just to point out that, let's see, so we started out with 1.8 liters at 1 atmosphere. We know we increased to 4 atmospheres, so that's an increase in pressure. So what do we expect? Since it's an inverse relationship, we expect the volume to go down, which it does, 0.45. All right, let's look at the second gas law, which is Charles's law. Charles's law relates volume and temperature. So in this time, we have pressures staying the same. Pressure's not changing. So Charles's law relates volume and temperature. Now, it's really important that it's directly proportional to the temperature in Kelvin. It has to be the absolute value, because first of all, you can't divide by 0. And since something can be 0 degrees in Celsius, we don't want to get to where we're going to divide by 0. But also, molecular movement has to do with the temperature, how fast the molecules are moving. So technically speaking, 0 motion of zero motion of molecules would be 0 temperature, and that only happens when we get to 0 Kelvin. So you do want to absolutely, whenever we're doing any gas law of any kind, you always want to convert Celsius to Kelvin before you do anything else. So, so here's the relationship. Volume is directly related to the temperature in Kelvin, as long as the amount of gas stays the same and the pressure stays the same. So that's constant. And since it's a direct relationship, as volume goes down, temperature goes down, or as volume goes up, temperature goes up. So they're directly related. And a direct relationship looks like this. V1 over T1 equals V2 over T2. There's a link to a simulation here that if you're watching if you want to do the video, the PowerPoints on their own, you can look at that. I think I may give you that. It may be an assignment as well to look at that simulation. All right, so here's an example, here's an example of Charles's law. So if we take a balloon, here we have well, here over here on the right hand side, we have two balloons that have the same amount of gas in them. If we take one of the balloons and put it into liquid nitrogen, which is very, very cold, the balloon will shrink. As it warms back up to room temperature, it will get bigger again. So directly related. Colder, smaller, warmer, bigger. Another example of Charles's law is a hot air balloon. We know when the air inside the balloon is heated, the volume of the balloon will expand because the pressure remains the same, because the pressure on the balloon is for the atmospheric pressure. And this is the relationship. So here, if you plot temperature versus volume, you get a straight line. And what they're showing you here is it doesn't matter what gas you have. Actually, they've got it in Celsius temperature, but notice that they all come back to zero, negative 273. So zero is zero. So 0 Kelvin is 0 volume. And doesn't matter what gas you have. So temperature and volume are directly related, which means temperature versus volume will give me a straight line. So let's look at a quick example with this one. A sample of methane gas that has a volume of 3.8 liters at 5 degrees Celsius is heated to 86 degrees Celsius at constant pressure. Again, no pressure involved, so that's good because there's no pressure in my equation. Calculate the new volume. So let's see, we have here, so I know this is my initial volume, this is my initial temperature, here's my final temperature, T2. Before I do anything else, I need to convert everything, and I'm looking for V2, final volume, or second volume. Don't forget to convert to Kelvin. So 5 degrees Celsius, you're going to add 273. It's 273.15, which is kind of a conundrum. You add that to get Kelvin, because if you just got one decimal place, you technically should round it to 2. A lot of people just forget the decimal at all and just add 273. So I'm not that picky about it. I guess let's just add. We could add the 0.2 if we want or not. It's not going to make a huge difference. So 270. So this would be 278 Kelvin. 86 plus 273 is 359 Kelvin. All right, so go ahead. I think what I did here again is I rearranged the equation before I did anything else. So I'm solving for V2, so I multiplied both sides by T2. Again, let's work over here. So if I want to, I can plug the numbers in. V1 is 3.8 over T1, which is 278, equals V2, which is what I'm looking for, over T2, which is 359. So if you want to, you can do this first. And you have the 3.8 divided by 278 gives me 0.01367. And then to get rid of the 359, I multiply both sides by 359. And of course that will cancel, and I'll have V2 equals 4.91. And then I would leave more sig figs and then at the end go back to what you started with. So 4.9, since my original liters is 2 sig figs, I would get 2 sig figs in my final. Or, like I said here, 3.8 times 359 divided by 278 gives me 4.9. And again, my Kelvin cancels, and I've got liters is my answer. If the volume was in milliliters, your answer would be in milliliters. If you're given two different temperatures, convert them both to Kelvin. You always have to convert to Kelvin anyway. And then let's just think about it. Our volume was 3.8. We increase the temperature. Since it's a direct relationship, we're going to increase the volume as well. So 4.9 makes sense. Okay, so our final relationship is the Gay-Lussac's law, and that relates pressure to absolute temperature if volume is kept constant. And again, it's a direct relationship. Pressure is directly related to temperature as long as your moles and your volume stays the same. As pressure goes up, temperature goes up, and as pressure goes down, temperature goes down. So our relationship is P1 over T1 equals P2 over V2. An example of Gay-Lussac's law, one thing is you should wait to check your car tire pressure. Well, it depends. You probably notice if it seems like it's low pressure and then you start driving, it gets heated up and the pressure will increase. Sometimes I've had the low pressure light up, but then after I drive a little while it goes away. Another example is if you've ever opened an oven and you feel that kind of whoosh of hot air out, well, you know, you're heating up the air inside your oven. As you increase the temperature, the pressure is going to increase because it's staying closed. As soon as you open it up, that pressure that has built up will come into your face. Okay, so an aerosol can has a pressure of 1.4 atmospheres at 25 degrees Celsius. What pressure will it have if you heat it up to 1200 degrees Celsius? And we're going to assume the volume remains constant. In other words, the can won't explode. Good luck with that. But anyway, it's just a problem. So don't forget that you have to, it has to be in Kelvin. So if we add, that's not very light. There we go. If we add 273, we get 298 Kelvin. 1200 plus 273 will give us 1473 Kelvin. So you have to do that before you do anything else. Remember that P1 over T1 equals P2 over T2. So we can either arrange it like I did here. So P2, we're going to multiply by T2. Or like I said, if you want to plug the numbers in, you can say 1.4 ATM over 298 Kelvin equals P2, which is what we're looking for, over 1473 Kelvin. You're going to multiply both sides by 1473. Notice that the Kelvin cancels out and your answer will be atmospheres. And again, we can see that we're increasing the temperature, so we expect the pressure to increase, and it does. We can actually combine all three of the gas laws together. So this is probably the only one you need to remember. P1V1 over T1 equals P2V2 over T2. So it relates all three things. So this is sometimes called the combined gas law. In the event that all three parameters are changing, you can still do a problem. So again, as long as the two pressures are the same unit, the two volumes are the same unit, and temperature always has to be in Kelvin, you can use this problem. So let's look at a quick example. A sample of carbon dioxide occupies 4.1 liters, so that's my initial volume, at 30 degrees Celsius, so that's my initial temperature, and 650 millimeters of mercury, so that's my initial pressure. What volume would it occupy at 800 millimeters of mercury, so that's my new pressure, and my new temperature? And so I'm looking for V2. So that's what I'm trying to find. Again, we have to convert temperature to Kelvin. So this would be, 273 plus 30 is 303 Kelvin. And 200 plus 273 is going to be 473 Kelvin. So, can't draw 473 Kelvin. So you definitely have to convert those. If you wanted to, you can convert millimeters of mercury to atmospheres, but since they're both the same unit, it doesn't matter. You can use what you're given here. So again, what's our formula? P1V1 over T1 equals P2V2 over T2. Now see, we're getting more and more values here. So what I was going to say is I actually have rearranged the equation algebraically to solve for V2, and it's P1V1 times T2 divided by P2 divided by T1. So be careful because the T's are going to inverse. And then I plug the numbers in, and again, the millimeters of mercury will cancel, the Kelvin will cancel, and my answer will be in liters. So I could just multiply this out and divide. Again, 650 times 4.5 times 473 divided by 800 divided by, hit divided by again, 303. Or if you don't do that, make sure and put parentheses around that. So if you want to say divided by 800 times 303, make sure and put parentheses, because your calculator will take order of operations. And if you multiply, it'll actually end up putting the 303 on top. So be really careful. Every time you've got something in the denominator with your calculator, hit divided by again, or be really careful with parentheses. I should make that a little darker. Either way. Or I could, like I said, I could, if I wanted to, I could plug in, I could say P1 650 times V1 4.5 over T1 303 equals 800 times V, which is I'm looking for, over 473. And I could do the math, so I could do the 650 times 4.5 divided by 303 gives me 9.653. And if I take 800 divided by 473, I get 1.691. And then if I just divide both sides by 1.691, I get the answer, which is 5.7 liters. And again, sig fig, since I had 2 to start with, I end up with 2. This one's a little harder to tell if my answer is right or not, because I'm increasing the temperature and I'm increasing the pressure. So, pressure inversely relates to volume, temperature directly relates. So turns out that I guess the bigger temperature change will increase the volume. You can't always check yourself. But anyway, that's another way you can do it if you like that better, rather than solving algebraically first off. All right, one other relationship is Avogadro's law. And Avogadro's law says that if you have equal volumes of any two gases at the same temperature and pressure, they will contain the same number of molecules. Or in other ways, they have a similar mole, the same number of moles of gas. So the volume of 1 mole of gas is called the molar gas volume, funnily enough, and it's given the symbol Vm. And it turns out, so if you've got gases, oftentimes we compare volumes at, if you see the words STP, see the abbreviation STP. STP stands for standard temperature and pressure. Standard temperature is considered 0 degrees Celsius or 273 Kelvin, and standard pressure is considered to be 1 atmosphere pressure. So if you're ever given a problem where all it says is STP and doesn't give you the temperature and pressure, realize that's what it stands for. So we can compare gases often at standard temperature and pressure. And here's an example. So whether we have helium, which weighs 4 grams per mole, or ammonia that has 17 grams per mole, or oxygen, which weighs 32 grams per mole, if we have 1 mole of any gas, no matter the weight, we will have the same volume. It'll expand to fill the same volume. And you can plug in, there's a way to do it. You can plug in standard temperature and pressure and solve for volume, and I'm not going to do it, but a molar volume, 1 mole of any gas at standard temperature and pressure is 22.4 liters. So 1 mole, 22.4 liters. So this means the volume of a sample of gas is directly proportional to the number of moles of gas. So far we've said volume is related to pressure and temperature, and it's also now related to how many gas molecules we actually have. So this is the direct relationship. Volume is directly related to the number of moles. Number of moles is given the symbol little n, number of moles.